In this video, I want to discuss the main function in MATLAB that is available to solve all kinds of linear systems. Now, before I discuss this function, let's take a look at the different methods that we discussed within this video lecture. And the idea of all of these methods is the same. So what we want to do is we want to solve this linear system AX is B, where A is an n by n matrix for x. So B is given, A is given, and we want to find x. The first method that we discussed is Gaussian elimination. And Gauss does convert this matrix A into an upper triangular matrix A over here. And this also has effect on the entries of B, of course, because we have to apply the same operations to the rows of A as to B. And in this way, well, we end up with a system that we can solve through back substitution, because the final equation is decoupled from the rest, and we can sequentially compute the solution and plug it back into the solution for the previous unknown. And that's back substitution. Then we had Gauss-Jordan elimination, and the main difference here is that we do not convert to an upper triangular matrix, but we convert here to this diagonal matrix, or this identity matrix to be more precise even, with ones on the diagonal. And the process for this is also first doing Gauss elimination, then normalizing the pivots, and then also eliminating the non-zero entries above the pivot values on the diagonal. And when you do this, well, then the B vector immediately holds the solution to your linear system. But the operations that you do in Gauss and Gauss-Jordan are almost equivalent. For LU decomposition, we see that, well, we decompose A into two matrices, a lower triangular matrix and an upper triangular matrix. And solving the matrix system AX is B came down to solving these two auxiliary but much easier systems. And the main difficulty here was finding matrices L and U, for which we again had to do some kind of Gaussian elimination in the process. Now it's important to note that the computational cost of each of these methods corresponds to the number of operations, and for a matrix with n rows and n columns, I'm not going to go into the details, but this amount of operations is proportional to the cube of the amount of equations that you have, so the amount of rows of the matrix. So let's say that for a matrix with 10 rows, that this would take 1 millisecond to compute. Well, that means that for a matrix with 100 rows, well, this would take 1 second. For a matrix with 1,000 rows, so that's times 10 in n, means times 1,000 in time. This would take already 1,000 seconds, and systems with 1,000 unknowns are very, very common. For 10,000 unknowns, this would take 12 days. So we see that this is the computational cost of solving such linear systems as we go to larger and larger systems really explodes. And this means that, well, efficiency is really key in solving these systems, because it can get very expensive if you have a large system. Now, fortunately, in MATLAB, we do not have to code our own linear systems. So when you have a practical problem, you don't have to start coding your Gaussian elimination, although you have to do this for the exercises, as this is also a learning process. But when you have a practical problem and you want to solve a linear system, you just use the backslash operator. That's kind of no questions asked, because based on properties of A, this will select a suitable algorithm from a list of very highly optimized functions. And this is really the bread and butter of MATLAB, is solving these linear systems. That's where it's very good at. Because it has a very long list of functions. For instance, this is for a dense matrix A. It will check certain properties of A, whether it's square or not, triangular or not, permuted triangular, whether it's a Hessenberg matrix, and then based on that, it will use a highly dedicated solver for that specific kind of matrix. For instance, triangular solvers, LU solver, it was what we've seen earlier, but also other matrix decompositions such as Cholesky decomposition or an LDL decomposition, which are out of scope of this course. But please remember that when you use this backslash operator to solve a linear system in practice, you're actually using highly optimized code that takes advantage of the structure of your matrix.
Now let's have a look at the performance of the methods provided or the functions provided with the handbook for chapter 4, and let's take a look at how these methods compare against the MATLAB backslash operator. So in order to do this, I will make a new script, and let's give the script a name. So I call it benchmark linear solvers.m. Okay, so the first thing we do is we set the size of our matrix, and let's call this capital N, and let's start out with 100 entries or 100 rows and columns in the matrix. So let's initialize the matrix A as a random matrix with 100 rows and 100 columns, and the vector B with 100 rows. Now we will solve this system AX is equal to B using Gaussian elimination with pivoting, which will be done with this Gauss pivot function that is provided by the textbook. And we will also solve it using the MATLAB backslash operator. Finally, we check whether both methods give the same answer. Okay, so let's get to work. So how do we do this? Well, in order to use this Gauss pivot function, well, we call the function with arguments a and b, and this will give us the solution, and let's call this x Gauss. And then we use the backslash operator, so let's call this x backslash, and calling the backslash operator is as simple as a backslash b. Now these both solve the same system, so they should give the same answer. Well, numerically this will never be exactly the same because they use a different algorithm. So let's take a look at the difference or the error between both by looking at the maximum of the absolute differences between both vectors. This gives us a estimate as to how different that these two methods are, and let's output this to the window as well. Now, in addition to simply calculating it, we can time these solvers by using the tick and tock commands, and then MATLAB will give us an indication as to how much time has elapsed between calling tick and calling tock. Let's do this for both, and if I run this script now, we should get a estimate as to how long this took, and then we get kind of a measure for how much the solutions are different. So let's run it by clicking run, and we see immediately, well, both solvers are pretty fast, so in a fraction of a second we find the solutions. The error is quite small, 2 to the power minus 6. Obviously it makes more sense to kind of normalize this, so let's normalize this with the norm of x Gauss, for instance, and then we get an output, so a relative error of 10 to the power minus 14, so that's quite good. And we already see that this backslash operator is orders of magnitude faster than the Gauss pivot algorithm. This case is aggravated actually if we start adding more elements. So let's do this for 500 rows and columns, and we see here that this starts really taking some time, 0.7 seconds, whereas this is still lightning fast. Increasing this further, well, we see that this will really start taking a lot of time. This Gauss pivot algorithm takes more than 4 seconds, whereas the other one takes only a fraction of a second.